So for this section, starting on page 50, we're going to learn how to integrate by parts. All right, this is a kind of a follow-on from the product rule. Just it's derived from that. It's in the reverse order. So if we were to take, for example, some function u and some function v and differentiate them, using the product rule. All right, so let's say we wanted d dx of u multiplied by v. All right, it would be the first function u multiplied by the derivative of the second, which would be dv dx, plus the second function v times the derivative of the first, which would be du dx. All right, so what we're trying to do here is go in the reverse order. So one thing that we can do is clear out all those dx's. So let me multiply everything by dx. And we would have d of u times v would be equal to u dv plus v du. All right. So I can now, you can already kind of see a little bit of it, the u, v, v du and all that. But let me solve for one of these items, and that would be the u dv. So I would subtract off the v du, and I would have u dv is equal to, it would be d, and I'm going to write it now as uv, minus v du. All right. Now if I go to integrate, I can integrate both sides of this equation. All right. So if I integrate both sides, I'm integrating this beefy integrand on the right hand side. But when you integrate really anything involving an addition or subtraction, it's addition subtraction rules. It allows you to break up the integral into separate parts. So I'd have u dv is equal to the integral of d uv, I'm leaving a little space there for a reason, minus the integral of v du. All right, because you don't just anti-differentiate a d anything. There's an integrand there. There's an understood 1. All right. If it were the antiderivative of 1 dx, the antiderivative would be x, plus c, but it would be x. So right here is my x. So instead of it being the antiderivative of 1 being equal to x because it was dx, it's going to be uv because my variable of integration is quote-unquote uv. All right. So minus the integral of v du, and that's where our rule comes from. It's actually just the product rule expanded and then just reorganized and then reversed. All right, so the question is, okay, well, how is this useful? Well, it tells us that if we can break up an integrand into the product of two factors, depending on what those factors are, we might be able to come up with the solution to the integral. All right, so the little tips there, try letting dv be the more complicated part of the integrand and all that stuff. Basically, I kind of look at it like when you select, you're going to select two things when you're integrating by parts. You're going to select a u and you're going to select a dv. All right, so the u should be something that you can differentiate. All right, dv should be something you can integrate. And I'll show you why in a minute. All right, you should be able to integrate whatever you select as dv, and you should be able to differentiate whatever you select as u. All right. In the case of number one, you really, it's of kind of no help because you can differentiate and integrate both. All right. So I'll add a little addendum to that. All right. You can differentiate and the derivative makes it more simplified. So I'll say makes it simpler. All right. So you might look at it and say, all right, well, I have a choice between the x and the e to the x. Which one could I let be equal to the u? Well, I could let the x be equal to the u. I could let e to the x equal to u, be equal to u. I can differentiate them both, but which one will make things simpler? I think the x. So I'm going to let that be x. All right. I'm going to throw on a little addendum to the statement regarding integration, and that is you can integrate whatever you select as dv, you can integrate, but so I'll write and does not make things more complicated. So does not make more complicated. All right. So it may not make it simpler. It might just maintain the status quo, but it's not going to make things worse. All right. So here I'm going to let, so we already chose the x to be the u, so everything else is going to be the dv, and that's e to the x dx. All right, the dx is part of it. All right, so we certainly wouldn't want to put the dx in with the u because then I would be differentiating a dx. I mean, doable, but not something I'm interested in. All right, so then I'm going to differentiate with respect to x, the x, which is 1, and therefore gives us du equals dx. All right, through cross multiplication. I'm going to integrate. Now this is an indefinite integral, but I'm going to not put the plus c on because we know that we can consolidate plus c's at the very end. So I'm going to hold off on that. All right. We have the understood 1 in front of the dv. Antiderivative of 1 with respect to the variable is the variable. So v equals antiderivative of e to the x with respect to x is e to the x. All right, so now I'm going to apply my rule, which is, again, the integration by parts rule, uv minus the integral of v du. So I take my u. I'll use my highlighter. I take my v. And whatever I have as du gets substituted in also. So I'm looking at x. I'll use black here. X e to the x minus the integral of v, which is e to the x, du is dx. All right, so we were able to pull out some stuff. All right, so we cleaned it up a little bit. That x e to the x doesn't need to be differentiated. It's already accounted for in this process. It's just the e to the x dx that needs to be integrated, and we know that that's e to the x plus c. Tack on a minus sign. We have x e to the x. If you want to factor out a e to the x, by all means go for it, but not necessary. And so that would be our antiderivative. If you differentiate that, you'll see. All right. Now, before we get into number 2, I wanted to do just a quick side quest here. All right, maybe I'll just kind of throw it off at the bottom. A little side example. I always do this, to the point where I kind of wonder why I didn't put it in the notes, but especially since there's a nice available space for it. All right, so let's say, as an example, we have the antiderivative of just the ln of x dx. I mentioned this in day 1 that I would talk to you about where the antiderivative rule for this comes from. All right. So we have to select, it comes from integration by parts. You have to select a u and a dv. All right. Well, I wouldn't, I definitely wouldn't select ln of x to be my dv because I'm here for that reason. I don't know the antiderivative of ln of x. So why would I select that to be the thing that I would have to, in my first step, anti-differentiate? So that's going to be my u. The only thing left is the dx. So du gets differentiated to du dx equals 1 over x dx, but I'm just going to write that, I'm sorry, du dx equals 1 over x, but I'm just going to write that as du equals 1 over x dx. If I anti-differentiate, I get v equals x. So again, uv minus the integral of v du. All right, so u is ln of x, v is x, so x ln x, minus the v, which is x, du, which is 1 over x dx. So antiderivative of 1 dx, we got the x ln x minus. Antiderivative of 1 with respect to x is x, and so this is where our antiderivative rule for the natural log of x comes from. So we can rely on this as a fact because it's a parent function, ln of x, you know, sine, cosine, arcsine, and all that stuff. So those become rules, right? So it's only when we have something that involves those, but are not quite the same, that you have to get into one of these processes. But here I can just say, well, if a question asks me what is the natural log of x, the antiderivative, x ln x minus x plus c. Why? Because that's the rule, right? So with that in mind, I can look at number 2 and say, all right, I got to select a u and I got to select a dv. The u, again, should be something, when I select it, that is something I can differentiate and will make the problem simpler. All right. The dv is something that I can integrate and not make things more complicated. All right. So ln of x, if I differentiate that, 1 over x dx, that's going to make things simpler. I'd rather work with a 1 over x than an ln of x, if possible. All right, the dv would then have to be x squared dx. When I integrate that, 1/3 x cubed. Now there's different schools of thought on this. Some people will say, well, that's more complicated. Well, is it really? It's a monomial. It was a monomial. It's still a monomial. Right? It's not more complicated. It's just got a higher power. That's like saying the number 2 is more complicated than 1 because it's bigger. That's not really the case. All right. So uv minus the integral of v du. So 1/3 x cubed, I'm putting the v first, ln of x, minus the integral of v du. All right. So if I multiply these two together, here's my du, and here's my v, I'm going to end up with 1/3 x squared dx. Increase my exponent by 1, I get x cubed, divide by the new exponent 1/9. Everything else comes along for the ride. And you can see here, hopefully, that this follows the same form as the natural log of x. It's just got a little extra oomph to it. But it's still x ln x minus x, still the same structure. All right, so it's kind of a cool relation, which we wouldn't have been able to recognize if I didn't take you through this first. All right. So then the last one, x squared sine of x, u dv. Well, if I differentiate, I can differentiate both the x squared and the sine of x. All right, if I differentiate a sine of x, it becomes cosine x. That's not simpler. If I differentiate an x squared, it becomes 2x I mean, it's a lower degree function. That seems simpler, but then again, you can kind of look at it the way we looked at the last one and say, well, just because it's smaller, just because its power is lower, instead of a 2, it's a 1, does that really make it simpler? All right. I'm kind of looking at it more like, all right, well, I'm a little iffy on that. I do know that if I make dv equal to sine of x dx and integrate, I'm not going to make matters worse. All right, it's going to be negative cosine of x, which is not more complicated than sine of x. So maybe I didn't really simplify things, like in number 1 where an x became a 1. That was great. All right, but x squared became a 2x. All right, well, I don't know if that's simpler, but it's something. But I didn't make matters worse in my selection of dv. All right, that's really what we're after. uv minus the integral of v du. So negative x squared cosine x minus the integral of v du. So we have a negative that's built into the formula and then a negative that's in my v, so those two negatives will make a positive. v du is going to be 2x cosine x dx. All right, so now we're kind of at an impasse where you look at it and say, well, I can't do that. All right, well, what's the antiderivative? All the other problems, I was able to take the integral and just do it. It was, that's not it. It was so easy. What you have to do here is it's repeat the process. All right, so the x squared became a 2x. There's every reason to believe that if we took it a step further and carried out integration by parts a second time, we're reducing the power of the monomial. The power of 2 became power 1, become a power of 0, and all we'd have is a constant, and then we'd be able to anti-differentiate. So let's carry out the process again. Let u equal 2x, dv equals cosine x dx. So du is equal to 2 dx, and v is equal to sine of x. So again, uv minus the integral of v du. So 2x sine x minus the integral of 2 sine x dx. All right, so that's 2x sine x. Antiderivative of sine is negative cosine. So negative 2 times negative cosine is positive 2 cosine. All right, plus the c. And that was added on. That was the add-on to the negative x squared cosine of x. So it took a little doing, but we got there. It's that extra step that throws people for a loop, because what'll happen is, at least in the early going, until you get the experience, and then once you get the experience, you're good. But until you get that experience, there's that second guessing where you get through that first step and you get to this right here and you say to yourself, well, I can't do that. I must have selected an incorrect u. So let me go back and make this a sine. And then before you know it, you're staring at the same problem for like an hour, just going in circles. All right. So sometimes you just got to trust the process and carry it through, and good things will happen.